Yeah, so welcome also from my side, and I have the pleasure to announce our second user-contributed talk for today, which will be given by Max Firmbach from the University of the Bundeswehr in Munich, and we're going to stick to multi-level solvers, but switch from domain decomposition now to multigrid methods. So Max. Yeah, please go ahead.
Okay, I hope you can hear me. So thanks for the invitation. So yeah, I will talk about physics-based block preconditioning inside MueLu, and especially with a focus on sparse approximate inverses. And I'll try to apply these things, this theory, to beam to solid interaction scenarios. Just a short overview. So in the first step, I want to talk about the goal and the motivation behind all of this. In the second step, talk about some multigrid basics and also some building blocks inside MueLu to form a sure-type block preconditioner. In the third step, talk about sparse approximate inverses and how they help us with our problem. And lastly, I will show some application scenarios, so weak scaling studies and some engineering applications. So let's start with the goal and motivation. So beam-solid interactions occur in a wide range of scenarios. So what can you imagine? So basically, we couple 3D solids with one-dimensional beam elements in a mixed-dimensional coupling approach, and this can occur in a wide variety of engineering applications. So as you can see on the right side, we have composite materials where fibers interact with a matrix material. Things like that appear in steel reinforced concrete, but also in biomechanics. So you have, for example, collagen fibers in connective tissue that interact with each other depending on the load scenario. And what we recognize so far is that in simulating these things, that the time to solution is dominated by the cost for the linear solver. This is quite typical because this very specific application for now only use direct solvers to use the linear systems that arise. And of course, we want to enhance the solution time by switching to multi-level methods that are hopefully scalable. We will use MueLu and thus algebraic multigrid methods for its flexibility because it's purely algebraic. So we only have to put in null spaces and our system matrix or our system operator. But some challenges we will encounter is that our system matrix is highly ill-conditioned due to the discretization we are using and due to the penalty regularization we will apply. These things prohibit out-of-the-box block smoothing in general for this case. And to formulate our goal is a scalable algebraic multigrid method for beam-solid interaction problems in penalty formulation. And to give you a glimpse on how our system looks like, so as mentioned, we have a coupling of beam-like 1D structures with three-dimensional solid continua, which are described in the following linearized system. I can also color code this to make it a little bit easier. So we have a solid part that contributes to the kind of continua stiffness. We have a beam stiffness matrix in green, or degrees of freedom related to that. And we have coupling constraints which are induced due to a mortar type coupling approach. The important thing here is the penalty parameter epsilon. So our coupling gets better by increasing the penalty parameter, or at least gets more realistic. Problem is, by increasing the penalty parameter, we are also increasing the condition number of our system, and they're basically linear dependent on each other. And basically the the condition number increases and we are losing diagonal dominance of our matrix due to this increasing penalty parameter. And so challenges, as mentioned, we have a highly non-diagonal dominant ill-conditioned block matrix due to the penalty regularization. And our block matrix may also become non-symmetric depending on the beam formulation we are using. So proceeding to the second block, the Schur type preconditioning in MueLu itself. And I want to start with some basic ideas on multigrid. I'm not sure how many people here are experts in multigrid, so I will repeat some basic ideas. So the first idea is that when we precondition our linear system, we want to decrease the iteration count of our iterative solver, or at least make it converge to some extent. And the multigrid idea is to tackle errors that are residing in our matrix and that per iteration of the iterative solver may increase, decrease, or stay constant. We want to tackle these different errors on different grids or levels. Because we are algebraic, we are just calling them levels for now. And we have a system matrix, which is a block matrix, and we try to represent this system matrix on each of these levels to tackle different error components on each of these levels. And what happens here is that we try to smooth these errors on each level and try to regather information of these different submatrices into our fine level solution, which is matrix with the indices 0. So as already mentioned, we try to smooth out these errors on different levels. We do that with the so-called smoother. Smoother examples are, for example, the Jacobi method, Gauss-Seidel, or as mentioned yesterday several times, some polynomial smoothers as the Chebyshov method, for example. And we can combine all of this in a so-called recycle in terms of restricting and prolongating our matrix to these different levels. So in the end, as you can see, we have a lot of different components that make up the multigrid algorithm, and each of these components can be tailored to a very specific problem such that the method overall behaves better. And in this case, I want to mainly focus on the block smoother to get rid of the different error components on each level. So what we will do in the beginning is we will set up a block iterative multi-level preconditioner. So what can you imagine under that or with that? So outside we have a block method, which can be a block EuroTUG, a block USAVA, or a simple method. And inside we have to solve a certain amount of linear systems. For the 2x2 matrix, it's most likely to be 2 linear systems for each diagonal block that we need to solve, and we will do that with multigrid. So in the end, we have an outer block method and glue multigrid methods internally together to obtain a solution for our block system. Of course, with this approach, we are considering the coupling constraints that you have seen, so the off-diagonal blocks only on the fine level, which might be a problem later on. And there are different approximations in this block method we have to choose or we need. So the first step is, as mentioned before, we have a very ill-conditioned system, so we can't use block Jacobi or block Gauss-Seidel for the block method as an example, because our matrix is not diagonal dominant, so these methods will fail. So we're only left with some kind of factorized approach, which includes the Schur complement. And when I go a step back, you can see the block matrix consists of a submatrix or single field matrix A, C, and B in a very simplified approach. And forming the Schur complement, I need to approximate the inverse of one of these diagonal matrices. So I'll just say, okay, we need an approximation of a power minus 1, the inverse of a, which we will call a hat. And this matrix is needed to form the Schur complement. And depending on which physics problem you have or what you know about like these algorithms, often the matrix is just approximated by its inverse of the diagonal. For example, the simple method for Navier-Stokes, a very common choice, is exactly this approximation. But we will see later on that in our case, this is not sufficient, because just using the diagonal for the inverse approximation leaves out a lot of information of the matrix itself. And in the second step, we need to approximate these block or sublinear systems in our block method. And we will do this by standard AMG, and we can tailor this AMG with user parameters to work in a certain manner for us. And maybe visualizing this, how this is working out in MueLu itself, without going too much into detail. So MueLu is based on a factory software pattern, which means every kind of block of functionality in MueLu is a so-called factory. And you can combine all of these factories that exist to make up a multigrid algorithm that is most likely work best for you. And describing how these blocks mover, for example, is made up, you can see on the top level, we have a blocks mover factory, and this can include a block LU, Usava, or simple type algorithm. And this blocks mover needs as input information about the subsolves it will do due to the algorithm. So we have to define smoother factories, 2 of them, which resembles the 2 linear systems we have to solve in the block method itself. And the smoother factories itself need some kind of operator where the linear solve is performed on. And on the left side, for example, you see we define a subblock factory 2. And this subblock factory 2 will extract one of the diagonal matrices of our block matrix, for example, the beam part. And it will make an operator out of it, give it to the smoother factory, and the smoother factory generates an operator smoother for this type of matrix and give it to the block smoother itself. The more complicated part is on the right part, where we also extract a subfactory, but we need to solve a Schur type system at some point in our block method. So this subblock factory extracts, for example, the solid part, gives it to an approximate inverse factory, where we can choose if we want to approximate with a diagonal, with lumping, or with sparse approximate inverses. We'll give it to the Schur complement factory, which calculates the Schur complement of the block matrix. We'll give it to the smoother factory, which in the end is used in the block smoother factory. So this is already quite complicated in some sense, but it shows the essential of MueLu and its flexibility. So you have different factories that in the end make up our block smoother, and all of these factories can be specified with an appropriate XML file, which is the main input to MueLu itself. And of course, each factory has several user-specific options. So if you're really into multigrid and you have a really complicated problem, you can specify each of these factories inside your XML file and make a very, very specific multigrid preconditioner for your problem. But of course, you can also do that much easier. There are facade classes which hide all of these complicated things. And you can also just use an XML file which considers 5 lines, which contains only the very basic information you need. So which smoother you want to use, which restriction and prolongation, and which multigrid type in general. So you have a lot of options to choose of. And of course, depending on the problem you have, you might want to go a little bit deeper and make it more user specific. So with this, I want to highlight sparse approximate inverses for our problem. So due to this penalty regulation I talked earlier about, using just a diagonal approximation, either with just a diagonal or with lumping approaches of the inverse inside this true complement calculation is not sufficient, because the inverse, of course, contains a certain information of our matrix. Just using the diagonal in a non-diagonal environment is quite crude, and a lot of information gets lost because the off-diagonal values play a major role here too. So sparse approximate inverse methods can help here to produce a better approximation. And what can you think about? What is this? So basically, you can just think of it as choosing a matrix graph, for example, of A, which defines the sparsity pattern. And on this sparsity pattern, we will try to calculate the inverse on. And of course, due to the choice of the sparsity pattern, this is not the exact inverse, but it's some approximation. And of course, we want to try to get a really good approximation. And this is based on a Frobenius norm minimization. So if you look at this kind of residual equation on the left side, if you multiply A with its inverse, you will get the identity matrix. And if you subtract the identity matrix in an ideal world with a perfect inverse approximation, you will get some kind of zero. But of course, this is not realistic. So we try to minimize this under the Frobenius norm to get some kind of good approximation in terms of the sparsity pattern we choose. And the sparsity patterns we can choose are here, this is called just S, which is the set of all sparse matrices with some known structure. And we can pick some known structure and try to approximate the inverse on this. And what I want to highlight here is that this method is inherently parallel, which means we can decompose this method into several least squares problems. And for each matrix row, we independently solve one least squares problem, which is in the end just a QR decomposition. Of course, all these rows can be independently calculated of each other, but in the beginning, we need to transfer some information of other values. So we have one communication step in the beginning, which depending on the sparsity pattern can be quite inexpensive. And after that, we are completely parallel and everything is independently of each other. So in an optimal case, you have an n by n matrix, you have n processors. Every processor can focus on one matrix row, and you can easily calculate the approximate inverse. So also the choice of the sparsity pattern, of course, has a big influence on the quality of the approximation. And just using the sparsity pattern of our input matrix A that we want to invert is a very trivial choice. In many cases, it's already a good choice, but for us, the results were not very satisfactory. So we try a very empirical approach that turns out to be quite good and efficient. So we use an static approach by using recursive powers of our matrix graph A. So what does that mean? It just means we multiply A with itself, and then we take this graph of our multiplication, which is enriched. So it turns out to have more values, or yeah, it's the sparsity pattern itself has more values than the one before. So we have more values to use for the inverse approximation. But of course, with this approach, using more and more recursive levels by enriching this graph, our calculation gets also more and more expensive because you're getting a more and more dense matrix. So of course, there's a trade-off between efficiency and approximation quality. And we don't really have to do this multiplication explicitly. We can just focus on we call it symbolic phase. So just combining rows of our graph of matrix A and obtaining the respective graph of the multiplication. And additionally, we will do a pre and post filtering of our input graph just to get rid of explicitly stored zeros and very small entries. And our overall algorithm for this inverting process in the end reads the following. So we do a thresholding of our input graph of matrix A. We determine graph powers of A to enrich the sparsity pattern. We calculate our sparse inverse on it based on this Frobenius minimization approach. And in the last step, we do a post filtering of our approximate inverse. And with this, we get a really, really good approximation of our Schur complement, which is essential for a converging method in our application case. So finally, let's have a look at some applications. So as a very minimal working example, I want to show this solid block with a random fiber placement inside. So what you can see is just a cube, which are solid elements with a hyperelastic Solvenau-Kirchhoff model. And inside there are just 1D beam elements, torsion-free Kirchhoff-Loff beam elements that were placed randomly inside. At the bottom surface of this cube is fixed, and we have a tensile surface load on the top side. So when we do the simulation, our cube will be elongated on this axis. And what you can also see, we have pretty much 25,000 solid degrees of freedom, 1,500 beam degrees of freedom, and we'll just start with one processor, and then we try to scale up. And how does the scaling look like? So I've showed you the 1 by 1 by 1 domain, which are about 25,000 degrees of freedom, and then we just multiply by 8, so each dimension is doubled, and you can find this original problem inside the bigger problems. So we just extend the domain and add more fibers to it, but inside the original cube is still maintained. We just elongate our domain. And as you can see, it's just a multiplication by 8 overall, and we scale up till we reach 1,000 processors, which is the kind of the maximum our cluster can take at the moment. So not heavy supercomputing, but still very much for us, for our resources that we have. So here I just want to highlight the hierarchy we build up, and I want to focus on the right-hand side column. So we do weak scaling study, so we expect the averaged workload of each processor to stay nearly the same. And if you have a look at the numbers, of course, we see a slight decrease in the overall degrees of freedom per processor. But I will say that is more likely constant and sufficient for our case. And also to show an example of the domain decomposition we are using. So we're using a geometric bisection. And the important part here is that each of these partitions has a certain amount of solid elements, but also beam elements. So each processor has some part of beams and solids to work on, which is quite important for the algorithm. It won't work properly if you have a partition that is just using solid elements on a certain amount of processors and only beam elements on a certain amount of processors. So we need this mix kind of solids and beams per processor. And showing the results, we plot the iterations and the solver time over the number of parallel processors. Maybe focusing on the iterations first. You can see that in the beginning, maybe going up to 300 processors, we see a quite increasing iteration count. So the method is not scaling very well there. But for higher core counts, we kind of can see that it flattens out and might stay constant overall. So sadly, we can't go right now to further number of processors, which might be interesting to investigate at some point if it really stays constant at that point. But at least for what we have now, we're quite satisfied with the results so far. Looking at the average solver time, this is of course not optimal. I'm using a BiCG step method here because I ran into some memory problems at some point. Of course, our system is for now symmetric, but anyway, we can see an increased solver time for each problem, which is not optimal. So I would have liked to see a more flattened out graph. But for the beginning, we are fine with that, and we are investigating the behavior a little bit further, especially this very linear behavior overall. So what's next? Another very nice problem is the composite plate. So in the problem before, we had a high amount of solid degrees of freedom compared to beam degrees of freedom. And what is interesting for us is what happens when we change that. So composites have this really nice feature that there are a lot of fibers and not a lot of matrix material. So modeling this is quite easy in the sense of you don't need a lot of solid elements to represent your continua, but you have a high count of beam degrees of freedom because of all the fibers that reside inside. And of course, this works quite well, but when we want to do a scaling study with this, by just elongating the plate, we also elongate the fibers inside this plate. So if you would imagine you double the length of the plate and the width of the plate, the fibers that run over the whole domain are longer for each problem that sizes up, which also means that the beam elements you need to represent this fiber are also increasing, which overall changes the sparsity pattern of our block matrix. And getting this to scale is a little bit difficult because the matrix structure, at least for the beam part, changes from problem to problem. This is not as trivial. We already have some results that are preliminary, where we can see that it scales at some point, but it's a little bit of tuning parameters that still has to be done, and some other problems unrelated to multigrid. And maybe showing an example why this is important also for the real world and not only from a mathematics side of view. So at our institute, we have a lot of people that work with concrete and modeling concrete and applying things to structures that are made out of reinforced concrete. So you can see here a beam that is pressured under this 4-point bending test. And we try to solve this with our preconditioner, which turned out to be quite well. Of course, the degrees of freedom we are solving here are not a lot, but even the direct solver that was used before had quite some struggle to solve this very efficiently. And even for the slow amount of degrees of freedom, the preconditioner we are using is quite competitive to the direct solver. And you can also see that for this case, the penalty value is 1,000, which is quite high in this case. So the matrix is very ill-conditioned at that point. So short little outlook. So what I presented now is just that we have a block method that wraps certain amount of AMG V cycles inside. But of course, what we want to achieve is a multigrid method that encapsulates the block method, so that we really take our block matrix and restrict and prolongate it through all the levels to be able to also consider the coupling constraints of this mortar type on all levels, which should reduce the number of iterations and give a better approximation to all of this. And the little tricky part is also the assembly of the beam degrees of freedom null space, which is highly specific to the beam formulation. So for now, we only consider torsion-free Kirchhoff law beam elements. And as you've seen, I think, they're sufficient for a broad range of applications. But a problem is that they are restricted to a straight center line in reference configuration. So they have to be stress-free at the beginning of the simulation. Of course, the goal is to extend this to other beam formulations too, which are already there in our multiphysics code, but it just needs some time and tweaks to be able to use that properly in combination with MueLu. With this, I want to thank you all for participating, and I want to also highlight my collaborators, which is Matthias in terms of MueLu, of course, Alexander Popp and Ivo Steinbrecher, who did basically the main contributions to discretizing and getting this beam to solid coupling things starting. Some references, of course. So there's an open source implementation available in Trilinos MueLu regarding this sparse approximate inverses, blocks, movers, etc. And not everything is yet available, but I will do my best to bring that to MueLu as soon as possible. That's what I always say. Let's see. And if you have questions or remarks regarding block preconditioning in MueLu, of course, you can contact me. And you can also have a view on our website, which might be interesting for other research areas and so on. So thanks for having me.